Hello family. I'm going to be going over the solutions for Can You Do 52. Before I get into that though, I just want to talk to you a little bit about these solutions videos, and please resist the urge to fast forward. So I am hoping that exam 4 was a little bit of a wake-up call for some of you guys in terms of the Can You Do. I've mentioned this before, and I think that it's worth mentioning again that when you guys are taking an upper level course, when you're taking a college course, a lot of your learning is at home. You have so much material to cover in one semester that oftentimes in class, your professor only has the opportunity to introduce you to the concepts. And how you really learn the concepts is by going home and doing the homework, which is why once you get to college, you will find that most of your textbooks, most of your classes are going to offer you a solutions manual, because there is this understanding that you're going to learn a lot from your homework. And in order to learn the most, you need to know whether your answers are right or wrong. Part of the reason why they do that, or why they are comfortable with or willing to give you the solutions, is because we're no longer at that point doing the homework for a grade. We are doing the homework for the learning. In college, most of your grade is based off of your tests, and then your homework is worth much less. And the reason for that is if we give you no points, the likelihood you'll do it is very low. So we want to give you points for the homework, but we want to base most of your grade off of your assessments, because that's how you show you learned the material. I am hoping that me offering you solutions to your assignments helps bridge the gap between what you're expected of now as a high school student and what you will be expected to do as a college student. I think that the benefit of this is twofold. One, it prepares you for college, and two, hopefully it allows you to see how beneficial doing your homework can be. And I think the video solutions are the best way to do it. Most of the time in college, you just have paper solutions. You actually look at a solutions manual, but I'm hoping being able to describe the processes behind these problems is helpful. So that all being said, I am hoping that exam 4 was a wake-up call, because I think a lot of what has been happening is copying the solutions that I'm offering you. I'm not sure how many of you guys watch these solutions videos. I know that they're getting used because I can see that the answers are getting written down, but I just don't know how many of you are actually watching them and learning from them. To get the most out of these Can You Do's, you really do need to try them first. You should not be watching this video right now with a completely blank Can You Do. You need to attempt the problems so that you know where your questions are, so that you know where you're getting lost, and then come to me for solutions, because then that will reinforce the learning. Realizing what you did wrong and then getting the solution for that is much more impactful than just watching the solutions and writing down the right answers, because you're missing that part where you have to think for yourself. So you guys are watching the Can You Do solutions, and then you're getting to the exam and you're not doing well because you skipped the part of your homework where you had to think for yourself. So a couple of things. When you watch a solutions video for your Can You Do's, you need to have attempted the problems. You'll get the most out of it that way. And two, just because you make it through a Can You Do, just because you were able to finish it with my help in video solutions and all of your notes, does not mean that you know the material well enough to do well on an exam. there has to be more than just the completion of the can you do. You have to go through it repeatedly to make sure you can retain the information and make sure you can do these problems without help. I mentioned it in the review video for 4 that if you are a kinesthetic learner, you learn by writing, you should be summarizing our units when you start to study for a test. If you're an auditory learner, you should probably be watching the solutions videos rather than the lessons, but either way, you can go back through and listen to the lessons again. If you are a visual learner, you'll want to go through your notes before you take your exam. So the biggest takeaways from the past 6 minutes are the following. It is not enough for you to just do the can you do with my help and with your notes. That doesn't indicate that you have the ability to think on your own when it comes to the test. You need to do a little bit more than that. 2, a lot of your learning comes from the can you do's. I can only show you so much in class. You get the other part through your homework. And 3, the only way that learning is going to be meaningful is if you try the problems first and then you come to me for help on the things you cannot do. If you just go straight to my solution videos, you are taking out the portion of your learning where you have to think for yourself. So then how do you expect to be successful on an exam where you have to think for yourself? I am hoping that most of you guys watched the last 7 minutes and have gotten something from it. So now that I have told you that you needed to have tried your can you do before you come here for solutions. Number 1, if you were not able to do number 1, if you struggled with number 1, that's reasonable. I need to go through some things in our notes to make some connections for you before you probably comfortable doing number 1. But other than that, the rest of the assignment, there should have been a fair attempt. So if you haven't done number 1 yet, you're fine. If you haven't read through it, I would read through it and see if you can. If you haven't done the can you do, I would stop the video and come back at 8 minutes and then go through the solutions. And if you've tried it and number 1's the only one that's not done, you're Gucci. We're ready to start going through things. So before we even get into the can you do, there is a couple of things in the notes that I just want to solidify because they are important, or I want to highlight because I didn't get a chance to highlight it in class. So the first thing is we went through and found a sampling distribution for a proportion. So this is our population distribution. We took 3 samples. We have 3 separate sample distributions. And then down here we talked about what the sampling distribution would look like if our sample size was large enough and it was a random sample. One thing that I should have done that I didn't do was explicitly show you how to describe what one of these points or p-hats represents. So in my made-up sampling distribution, this one sample here that I have circled represents a sample of 50 students in which 13% of the students were left-handed. I'm getting the 13 from the x-axis on my normal distribution. So this dot represents one sample where the proportion of left-handed students was 13%. So now when we look at can you do number 1, can you do 52 number 1, you can now do part A of that can you do. I'm just looking around for a blank one. I'm going to pause. If you haven't done 1A yet, do that now. Okay, so from this information here that I just filled in for you, you can now do 1A on this doing homework problem. So the dot represents, sorry guys, the dot represents one simple random sample of 100 students in which 73 students did all of their homework. How do I know it's 73? Because this dot is 73%. This dot is 73%. And 73% of 100 is 73. You could also say this dot represents one SRS of 100 students in which 73% of the students did all their homework. B and C are the ones where I think that you need a little bit more guidance. So B, would it be surprising to get a sample proportion of 0.45 or lower in an SRS of 100 when the true proportion is 0.6? Okay, now let me back that up a little bit and make sure that we understand what this dot plot is showing us. So what this dot plot is showing us is we have a population in which 60% of the students do or did all their homework. So we're starting from the claim, that P equals 0.60. We have here 250 simulated samples. So the proportion, the true proportion is 60%. And from this population where P is 60%, if we took 250 random samples, their distribution would look very similar to this. So I'm going to say that one more time. These samples, there are 250 samples here, 250 dots, came from a population where 60% of the kids did their homework last night. So they're saying, would it be surprising to get one dot? So to get a sample or to get one dot where the proportion that did their homework was 45%. So we take a sample from this population and we get 45% of them did all their homework. Would this be surprising? Well, let's go up to our dot plot. 45% is right here. So we simulated taking 250 samples from a population in which 60% of the kids did their homework. And out of all of those samples, out of all 250 samples, none of them had 45 or lower. Would we find it surprising then that we get a sample of 45 or lower? Yes. Yes, it would be surprising to get a proportion this low, because in 250 samples from this population, none of them were that low. None of them. It would be impossible to get a sample this low based off of this dot plot. So the heart of the matter is, yes, it would be surprising. So the way that I worded that was, yes, it would be surprising because none of the simulated samples above resulted in a p-hat of 0.45 or lower. It is not plausible to get a p-hat of 0.45 or lower if the proportion, the true proportion, is 60%. So pause the video and write that in your own words, or write this down if you need to. And then I am going to explain this one more time, because I found last year in this unit, this homework problem in particular, I think was the hardest problem in the whole unit for my students. So pause and write it down and then come back. Okay, I just want to discuss briefly what I mean here by it is not plausible to get a sample proportion this low if the true proportion is 60. So I just want to reiterate, these 250 samples have come from a proportion where, or have come from a population where 60% of the kids did their homework. So it is not plausible to get, or it's not reasonable, or it's not likely to get a sample of 45 or lower if it came from this population. So basically, it's impossible to get a sample where only 45% of the kids did their homework if it's coming from this population where we know 60% of the kids did the homework. That's too low. And then that leads into the next question, and they're almost the same. Part B is trying to get you to recognize that it would be very surprising to get a sample that low. Now, part C is asking us to frame that in terms of a claim. So suppose that 45 of the 100 students in the actual sample say that they did all their homework last week. What would you conclude about the newspaper article's claim? Explain. So the very beginning of the year, we talked about how you can use your dot plot to decide if you have convincing evidence against a claim. And the cutoff for that was 5%. If something happens more than 5% of the time, then it's reasonable. We don't have convincing evidence. But if something happens less than 5% of the time, we have convincing evidence. So, in this case, the percent that we're using, or what we're finding, and you don't have to write this down yet, is what percent of the time did we get a p-hat less than or equal to 45? Well, we discussed this in the last problem, 0% of the time. Out of 250 simulated samples, none of them were this low. So 0% is definitely less than 5%. This is convincing evidence that the claim is not true. The newspaper article is claiming 60% of the kids do their homework. If that were true, their sample distribution would look like this. And out of 250 samples, we never got one that was that low. So the fact that we're getting one that is that low says your claim is probably not true. There's no way to get 45% if you took it from a population of 60%. 60% of the kids did the homework. So the sample exists. We got the sample, which means that the claim is probably wrong. So how we word that is, there is convincing evidence against the newspaper article's claim. Based on the dot plot above, the percent of samples that had 45% or less students complete their homework is 0. So it is not plausible to get a p-hat of 45 or less if p is 0.60. So I want to reiterate, sorry, I'll uncover that so you can pause if you need to. I just want to reiterate what I said before, that of this entire unit, I feel like my AP kids for 2 years in a row now find this problem to be the hardest, to understand this idea of we claim the population is this, we're going to take a bunch of samples, here's what they might look like, and then use that to decide if a claim is true. If you are struggling with this problem, that's normal. Hopefully me telling you that this was the hardest problem for most of my students to wrap their mind around makes you feel a little bit better if you're sitting here going, I don't understand what you're saying. So the best that we can do is keep trying problems like this, talk to a friend, come talk to me, ask another teacher, Google it up, see if there's a different video that describes convincing evidence that would make sense to you. If you're struggling with this, the best thing that we can do is just try to get as many examples as we can and see if over time our understanding comes. So if you're confused now, the best thing that you can do is ask me or ask a friend or ask another teacher or Google it. It is normal for this to be confusing, but I'm hoping that the discussion in this solution helps some of you guys. Okay, so that's number one. Number two is doable. So we have a small internet mail order company that keeps track of the number of orders it fills over many years, and then we run the 5 summary statistics on this. So this information that you're getting right here is the population statistics, is the true information from the population. They averaged out how many orders they filled per day for years, so probably more than 1,000 days, and got these summary statistics. Now they're saying from this population, we take random samples of size 40 and we calculate the range for each sample. So what they want us to look at is the range. So first thing is, what is the range of the population? So I'm going to write that up here with the rest of the information. The population range. Okay, remember, range is your max, subtract your min. So our population has a max of 80 and a min of 20. So our population range is 60. We take a bunch of samples. It says we take 50 samples. This is the result of the 50 samples. What you calculated for each sample was the range of your sample. So the maximum number of orders you filled, subtract the minimum number of orders you filled. So up here, when it says random samples of size 40, what this means is they looked at 40 days. They took the maximum number of orders filled in that 40 days, subtracted the minimum number of orders filled per day in that 40 days, and found the range. There are 2 dots on the graph at 53. Explain what these values represent. So here. So what that represents is that there were 2 random samples of 40 days in which the range of orders delivered was 53. So we had 2 random samples, and the range of orders delivered on those days was in those samples was 53. Okay, the next one is related to bias and the shape of the sampling distribution. So, is the sample range an unbiased estimator of the population range? Use the dot plot above to justify your answer. So, one thing that I want to revisit, because we didn't have very much time to talk about this in class, and I'm going to write it on a Post-it note, is how we can get a quick idea of what our mean, our average of a sample would be. So, if you have a distribution and it is symmetric, what this tells you is that you can quickly look at this distribution and know that your mean is equal to your median. This is helpful because sometimes you get a distribution that is very large, like thousands of numbers, and it's not reasonable for you to add up thousands of numbers to find an average. When the alternative is you can just look at where the center of your distribution is and get a good estimate. So if you know that these two things are equal, you can quickly identify what the average value might be without having to add a bunch of numbers up. The other thing that we know is if you have a skewed distribution, those values will not be equal. Sorry, I'm just trying to get a good skewed distribution here. So, in the case where it's right skewed, your median is here, your mean is usually to the right. And in this case, your median is here, and your mean is usually to the left. Okay, so this is from this page. So I may just add this Post-it note to this note page. We had an example of our gymnasts in Can You Do 51. We had a problem about walking on our hands. And it wanted to know if our sample was an unbiased estimate of the true population mean. And in this case, we cannot use the shape of the distribution to decide, because your median is here, which means that your mean is somewhere to the right of it, so you actually have to calculate your mean. So sometimes you're going to get a distribution and the mu is not going to be at the center. If your distribution is skewed like this one, your average value is going to be to the left. So in this case, your median was 21.5, and your mu sub x bar is 20. That is this situation right here. Your mu is to the left of your median. So, this is all to say, when they try to talk about bias, often what it leads you to believe is that the center of your distribution has to equal the population parameter. And that's not the case. It's not the center that has to equal the true value. It's the average. The shortcut is this. This is a shortcut. If you're lucky enough to get a symmetric sample, then your median and your average are the same. But what we must keep in mind is that we're not looking to see if the center equals the true value. We're looking to see if the mean equals the true value. So in this problem, if all we thought was, okay, the center has to equal the true value, we would say that this was a biased estimator because our center is 21.5. We can't use the center though because this is skewed left. So we actually have to go through and find the mean of this distribution. The mean of this distribution is adding up all of these numbers and dividing by 10. So to be really clear, if we wanted to find the mean of this distribution, the mean of all of the x bars, you would add 14 plus 21 plus 23 plus 22 plus 15 plus 17 plus 16 plus 24 plus 23 plus 25 and divide that all by 10. That ends up being 200 divided by 10, which ends up being 20. So the mean of all of our samples was 20. This is equal to the true value, which means that this is an unbiased estimate. So I went through all of this stuff because I'm trying to highlight to you that they're not looking for if the center is equal to the true value. They're looking to see if the mean is equal to the true value. And in this case and this case, we just get lucky that the center and the mean equal. Hopefully that helps. So, back to the problem that we're actually on. Is the sample range an unbiased estimator of the population range? Use the dot plot to justify your answer. You have two options. You can add up all of these dots. So you can plug into your calculator 53, 53, 54, 54, 54, 54, blah, 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 blah. And then run the one variable stats and actually find mu sub x bar. Or you can look at the shape of the distribution. The shape of this distribution is approximately normal, which means that your mu sub x bar and your median are going to be about the same. So instead of adding up all of these numbers and dividing by 50, I'm just going to find the center of the distribution. And the center of this distribution is 57. Now, I'm pretty sure that if you find the actual mu sub x bar, it's 56.8 or 57.8. I didn't do it, but I will right now. I'm going to do it right now. I'm going to pause and actually plug this into my calculator and find it. Okay, so I went through and did it. We got our median to be 57. If you entered in all these values and used your calculator to find the mean is 56.78. So these are approximately equal. So just to reiterate, this is the mean or the average of all of these points. okay? So is the sample range an unbiased estimator? It is unbiased if the average of your samples, so the average of your samples is equal to the true range. Now, why did I not say mu sub x bar here? Because our samples are not giving us the sample average. These are ranges. This is a range of 53, a range of 54, a range of 55. So the average of our sample, I guess I could say sample ranges, needs to equal the true range. Well, our average sample range is 57. Our true range is 60. So this is a biased estimator. This is biased. So how do we word that? Well, the estimate of our range, so from our samples, is about equal to the median of our samples. Why? Because this distribution is approximately symmetric. So I did a shortcut, and instead of entering all those into my calculator, I said it's going to be about 57. Well, the range of the population is 60. So the sample range is not an unbiased estimator of the population range because the mean of the samples, or the sample ranges, is not equal to the range of the true population, or the true range. Okay, those two problems are the bulk of the information that would probably help you understand this a little bit better. So from here on out, it gets a little bit quicker. So breakfast cereal includes a bunch of shapes. Sketch the population distribution of the marshmallow shapes. So this is categorical data, which means you can have a pie chart or a bar chart. So I drew a bar chart with relative frequency here, and then these numbers are the percents in the bars. So suppose you were to collect a random sample of 2,000 marshmallows. Sketch the distribution of your sample. So here's the thing. If we go back to our notes for this lesson, essentially what they're asking us to do is this. We have a population distribution that looks like this. And we took 3 random samples, and each one ended up being different. These look similar though. Like, look how close this bar chart is to this one, and this one is to this one, and this one is to this one. So if we take a sample from this population, we're expecting that the sample is going to look similar to this. Are we expecting that it's going to look exactly the same? No, because of sampling variability. It is very rare that we would take a sample and get this exact distribution. So what I did instead was I just adjusted my percents a little bit. You can draw the same exact thing if you wanted to, and I wouldn't mark you wrong. It's just not that accurate. We would not get a sample that was exactly the same as the population. That's very rare. But we would get one that was super close. So I just adjusted my numbers a little bit. So instead of 10% for my stars, I changed that to 12. I kept my moons at 10, but I adjusted my rockets up to 21%. I adjusted my astronauts down to 39, and then to make sure that they all equaled 100, the planets had to be 18. So what would I expect my sample to look like? I would expect it to be very similar, but not exactly the same. So then what I have in red is the number of shapes out of 2,000 that would be. So 240 of the 2,000 shapes would be stars. The last question says, how many rockets would you expect to see in your sample? Well, I would expect that about 20% of my sample would be rockets, because 20% of the population is rockets. So I said I would expect to see about, not exactly, but about 400 rockets in my sample. If this were my true sample, I got 420, close enough. 400, 420, it's about the same, especially out of 2,000. That's not a huge difference. So I would expect to see around 400. And then our last question is, now suppose you collected many samples, sketch the sampling distribution of the proportion of rockets you would expect to see. So notice, here they're asking about the whole distribution, every shape. Here they're asking about the whole distribution, every shape, but then asking you to focus on the rockets for the number of or for the percentage of rockets that you would see. So they want you to sketch the entire distribution, but then specifically look at the rockets. Now they're saying you take a bunch of samples and only look at the rockets. What would that sampling distribution look like? So that's this. We have a population, we take a sample, we focus on how much of these samples are rockets. So in that case, our sampling distribution would look very similar to this. Proportion of rockets in the sample. You would expect the center of your distribution to be 20% because that's the true population value. And then you would expect most of your samples to be clustered around 20%. So it would be a normal distribution. You don't have to get any more specific than this. So the biggest thing we want to take away from this is if our population looks like this, our sample is going to look very similar. And if we take a bunch of samples, if the only thing we're focusing on is the rockets, the distribution would be centered around 20%. If they were asking us about the astronauts instead, the distribution would be similar, but this would be 0.40 and the label would be astronauts. If they were asking about the planets, it would look like this, but we would say planets instead of rockets. Hopefully that helps. And then our last questions are the multiple choice. So in number 4, A and C are similar, but what we need to keep in mind is that the 78% is describing a parameter. You get a parameter from a population, but 78% is not the population. The population is the individuals in your sample. The parameter is the actual percentage. Same here. The sample is the group of individuals you took from the population, and what you get from the sample is the statistic or the proportion. So C as in cat. 5, a statistic is an unbiased estimator of a parameter when in many samples the values of the statistic are centered at the value of the parameter. The reason why it's saying centered is because if you have many samples, your distribution will be normal. If you only take a few samples, your distribution probably isn't normal. But if you take many samples and you plot that out, your distribution will end up being normal. Why, in the case of our gymnastics kids, did we get a skewed distribution? Because 10 samples is not many samples. Even though that's the total number of samples we could take, that's not enough samples to give you a normal distribution. You would need to have a lot of samples for your distribution to be normal or be symmetric. So a statistic is unbiased if the center is equal to the value of the parameter, but that happens when you have many samples. And it doesn't only happen then, but it will always happen if you take many random samples. Your distribution will be normal. In a residential neighborhood, the median value of a house is 200,000. For which of the sample sizes is the median most likely above 250 samples, or 250,000? For which of the following sample sizes is the median most likely to be above 250,000? So this is the true value. This is the estimated value. So we're looking at a distribution that is skewed right, where the true value is here and the estimated value is here. Well, I just got done telling you that if you take enough samples, your distribution is always normal. So if we're getting a skewed distribution, or we're getting a distribution where these two things are not matching up, our sample is not matching our population, then we probably have the smallest sample size. So you have A. The smallest sample size will lead to the most chance of you not equaling the true proportion, or your distribution being skewed. So the smaller the sample, the harder it is for the estimate and the true value to equal. Increasing the sample size in an opinion poll will reduce variability. Remember, you cannot reduce bias. You cannot reduce bias. Bias is either there or it's not. It's a yes or a no. It's not a continuous value. Okay, so I know that these solutions were way longer than what you guys are used to, but there was a significant amount of things that I felt like I couldn't cover or didn't have time to cover in class. Hopefully you found these solutions helpful and it was able to clear up any questions that you have. Can you do 52 will be due the next time that I see you. I am happy to answer questions. So if these solutions weren't enough, please come ready with where you get off track or what is not making sense, and I will happily use class time to answer questions that you have. It may be helpful for you to ask a friend or Google it if you're really struggling. But like I said, if you want to wait till class, I'm happy to answer questions. Okay. Love you guys.